Welcome to the next chapter. So today we will discuss about the time response of the control system. Now the output of the system has two responses. Let us suppose that we write the output of the system. As you have studied, the output of the system has two responses, that is the forced response plus the natural response. Forced response plus the natural response. Now the forced response is also called the steady state response or the particular solution. Forced response is also called the steady state response or particular solution, and the natural response is called the homogeneous solution. It is called the homogeneous solution. Now many techniques such as we have discussed, solving the differential equation or taking the inverse Laplace transform, enable us to evaluate this output response, and these techniques are time consuming. That is, we have that we have discussed previously, that we have the differential equation and we find the Laplace of that, and after that we solve that, and after we find the inverse Laplace of the differential equation. But this technique is very time consuming, and also one more point, that productivity is aided by the analysis and design technique that yields the results in minimum time. That is, the results should be obtained in the minimum time, so that the system would be productive, that is, analysis would be productive. And if let us suppose that we have a technique which is so rapid that we derive the desired results with only inspection, while only inspecting the equation, and we use that attribute qualitative to describe the method. So if the method is such that we can see the response, or we can see the system by inspection only, then it's very easy for us. Now one such technique is the pole zero technique. One such technique is the pole zero technique. So pole zero technique is such a technique that gives us the qualitative approach to the problem. That is, we will see the things qualitatively. Okay. So the concept of this pole and zero, these are fundamental to the analysis and design of the control system, and simplifies the evaluation of system response. It simplifies the evaluation of system response. That is, while looking at the system transfer function, we can simply analyze and have some qualitative information about that system. Now come to the poles of the transfer function, and then we can discuss about the zeros of the transfer function. Now what are the poles of the transfer function? Then we will have the zeros of transfer function. Now let us suppose that we have a transfer function. Let us suppose that we have a transfer function that is s plus 2 and s plus 5. Let us suppose fs is equals to s plus 2 and s plus 5. Now the poles of the transfer function are the values of the Laplace transform variable s that causes the transfer function to become infinite. That is, these are the values of Laplace transform variable that causes the transfer function to become infinite. In this case, if s equals to minus 5, then we can say that this transfer function is infinite. That is, s plus 5 equals to 0 and s is equals to minus 5. Okay. So as per the definition, this variable as minus 5 causes the denominator to be 0 and this whole of the transfer function to be infinite. Now we have seen that the roots of characteristic polynomial in the denominator are the values of s that makes the transfer function infinite. That is, the roots of this makes the transfer function infinite. So we can say that this is the pole. Now one more point is that let us suppose that the transfer function is like that, s plus 2 and s plus 5, and s is cancelled in this case. Now if the factor of denominator can be cancelled by same factor in the numerator, that is s, the root of this factor no longer causes the transfer function to become infinite. So this no longer causes the transfer function to become infinite. So we often refer to the root of the cancelled factor in the denominator as pole, even though the transfer function is not infinite. So even though these are cancelled, but still we called this as the pole. Okay. So first point is that is which makes it infinite. However, in such cases where these are cancelled by the numerator, still it can be called as the pole. Okay. Clear? Now come to the zeros of the transfer function. Now zeros of the transfer function. Now the zeros of the transfer function are the values of the Laplace transform variable s that causes the transfer function to become 0. That is, in this case you will see that on the numerator we have, if s is equals to minus 2, then you can say that fs is equals to 0. Okay. So the roots of the numerator, that is s plus 2, the root of this numerator are the values of s that make the transfer function 0. So these are known as the zeros. However, similar is the case with the poles. If the factor of the numerator is cancelled by the factor of the denominator, the root of this factor no longer causes the transfer function to become 0, and we often refer the root of the cancelled factor in the numerator as 0 even though the transfer function will not be equal to 0. So from this we can analyze that if the roots of the numerator can be obtained, then they will give the 0, and if the roots of the denominator is obtained, that is known as the pole, and 0 will make the transfer function as 0 and the pole will make the transfer function as infinite. However, if the common factors are there which are cancelled, still they are called pole and the zeros. Now let us consider a system, let us consider a small example in which we have a transfer function that is s plus 2 divided by s plus 5, and let us find the unit step response of this system. That is, it means that we applied the input Rs as the unit step and we will get Cs as the output. Now in this case, as you have done previously, Cs is equal to s plus 2 divided by s plus 5 into 1 by s. So Cs in this case is equal to Rs plus Gs. So solving by using the partial fraction expansion as we have discussed in the last chapter, and finally using the inverse Laplace transform, we will get this 2 by 5 plus 3 by 5 e minus 5t. Now this transfer function Gs we will plot on a S plane. Now it has the real axis and the imaginary axis, that is sigma plus j omega. Now this pole can be represented by cross and the 0 can be represented by this 0. Now as you see that in this case s plus 2 divided by s plus 5, so if we see in this case pole as s plus 5, the root of denominator, so pole is equals to, in this case is equals to s is equals to minus 5. So this is pole in this case, and 0 in this case is equals to s is equals to minus 2. That is, s equal to minus 5 will make the transfer function as infinite, so it is a pole, and this makes the transfer function 0, so it is the 0. So pole is minus 5 and 0 is minus 2, and it is plotted on a complex plane as shown here. Now previously that we have discussed a pole and a 0. Now pole in this case is, you will see the pole in this case is, that is s is equals to minus 5 that we have plotted in the previous diagram, and 0 in this case is s plus 2 which is here, and input pole is equals to 1 by s which is represented like that on the this axis, and input pole, that is 1 by s, s is equals to 0, so it is on at the intersection point. Now you will see that as in the previous example we have seen that this s plus 2 divided by s into s plus 5 is the total response, okay, and we bifurcate it by using the partial fraction expansion. So this 0 will contribute both A and B as shown in this diagram. That is, this 0 will contribute the things that is values on the numerator. Input pole will be Here input pole means that whatever input we have given, that is in this case it is 1 by s, and system pole it is here, that is s plus 5. Now after this transform, and after that transform we calculate the inverse Laplace transform. We calculate the inverse Laplace transform, and final result that we are getting is 2 divided by 5 plus 3 by 5 e minus 5t. So some observations can be made out of that. So we get the two responses. This is the forced response and second one is the natural response that we have already discussed. Now some observations can be made. The first observation is that is the pole at the input function generates the form of the forced response. That is, the input function pole generate the forced response. In this case we have considered as the step input. Now second one is that a pole of the transfer function, this is the pole of the system transfer function s plus 5, generates the form of the natural response. Now it generates the form of the natural response, that is s plus 5, it will generate e raised to power minus 5t. Also a pole on the real axis, that is minus 5, generates an exponential response of the form of e minus a t, where minus a is the pole location on the real axis. That is, let us suppose that pole is on real axis, that is minus alpha, that we have seen also as minus 5. So it generates a response of k e minus alpha t. Also one more point is that the farther to the left a pole is on the negative axis, the faster the exponential transient response will decay to 0. So this point is also very important point. One more point is that this zeros and these poles generate the amplitude of both these forced responses and the natural responses, which can be seen from the calculation of A and B, which we have calculated using the partial fraction expansion. So from this we can learn the art of writing the response by inspection, that is each pole of the system transfer function that is on the real axis generates the exponential response, and that is the component of the natural response, and the input pole also generates the forced response. Now we will discuss this example. Now here we have to evaluate that response using the poles. By inspection we see that since in this last sometime later we have seen that this input, this is the forced response in the output, and this is the natural response, that is poles will generate the natural response. So we will write the equation in this way: k1 by s plus k2 divided by s plus 2 plus k3 s plus 4 plus k4 s plus 5. In this case this is the forced response and this is the natural response, and we take the inverse Laplace transform, we will get this equation in time domain, from s domain to time domain. In this way, from seeing only the transfer function and what is the input at the transfer function, we can simply see the system, and we can simply see that what's its forced response and what its natural response. Now let us consider one more problem. Let us suppose that unit step. Let us suppose that we have a transfer function which is given by 10 s plus 4 and s plus 6 divided by s plus 1, s plus 7, s plus 8 and s plus 10. Now this is the transfer function, and if the input is unit step, and in case of unit step we have the input is 1 by s. Now we have to find the response by inspection only, that is from the pole 0 plot only. So as we have already seen in the first case, so 1 by s factor is also coming, and this 1 by x factor will give the constant value, that is a. Second, we have plus b, this will give the exponential response, that is e minus 1t, that is e minus t, plus c, e, this 7 minus 7t, plus d, this one e minus 8t, plus e minus 10t. So from this we will see that while only seeing that we can get the response of the this system. Also one more point, that is we have seen that this is exponential response 7t, 8t and 10t. Now as we have discussed previously, that more be the pole, that is farther be the pole to the left on the negative real axis, that is, let's suppose that we have the pole 1, 2, 3, farther be the pole to the left axis, that is negative left axis, real axis, the faster be the transient response will decay to 0. So it is further in this case, that is minus 3, minus 2 and minus 1, faster it will, the exponential transient response will decay to 0. That is, you will see that if this is first, second and third, then we can say that let it be the e minus t, then this be e minus 2t and e minus 3t, that it will reach 0 faster as compared to this and this. So further to the left a pole is on the negative real axis, the faster the exponential transient response will decay to 0. So this is all about the pole 0. So in this you can simply see that how we can give the qualitatively we can see the what the system is all about, and also write the equation in the time domain.